So a couple that you simply have to remember are these next two. And notice both of them are as x goes to 0. So on this first one, whatever's after sign and on bottom need to match. We'll look at some examples of that. And when that happens, the limit approaches 1. And then on this one, again, it goes to 0. And it's 1 minus cosine x. Again, these have to match. And we'll look at that one. We'll actually see this one a lot more than we see the second one. So those you actually do have to memorize. Now, moving on to squeeze theorem. You'll want to stop the video so that you can draw a picture of this. But this is a picture that talks about what's in squeeze theorem. So I have these two functions, h of x and g of x, that f of x lives between. And so you can see that in the picture. And so if the limit, so we know from squeeze theorem, if the limit of h of x as x approaches c, so notice this c is kind of important over here, and I drew a little open circle so we could see what was happening. So if the limit of the lower function as x approaches c is L, and if the limit of the pink g of x function as x approaches c is L, then by squeeze theorem, since f of x is in between them, the same has to be true for the limit of f of x. Squeeze theorem's pretty popular. Oh, I do want to backtrack and talk about the limit of sine of theta over theta. Remember I discussed with you when we were reviewing trig functions how tangent and sine are buddies, and so just as a note, because they operate the same way in so many ways, that that special theorem also holds for tangent. So as x approaches 0, the limit of tangent of theta over theta equals 1. Again, point to remember is that these must match. So just be on the lookout for that. Okay, so now moving on. Some ways to find limits. We can substitute and see what we get for an answer. But if the denominator equals 0, I can't try that. So then another strategy is to factor and see if I can cancel factors out. We've seen that once already yesterday when we were looking at the polynomials that factored. And then another option, we haven't seen this yet, but we're going to see some in the examples, is we could rationalize the numerator or denominator. And then, of course, you can always check by looking at a table and see what's happening as you get super close to the value that you're interested in. So let's turn the page and start looking at some examples. So on the first one, if I look at a graph of tangent of x and I look at what's happening as we approach pi, if you remember, this is what the graph of tangent of x equals. And so from both the left and right, as I get near pi, I'm approaching 0. So the answer to this one would be 0. And so that was just a direct substitution. If I look at the next one, and I tried direct substitution, and I put a 4 in there, I'll have the cube root of 8, which is 2. And so that one's not a problem either. So the limit as x approaches 4 of that function is 2. On this next one, so we're using some given information that we already know about some of the limits and using some of our limit rules. So remember, if I have a coefficient on here, I can pull it out. And so then I look at 4 and then times the limit as x approaches c of f of x. And then I say, hey, I happen to know this. It's 3/2. So I'm doing 4 times 3/2, which is 6. On letter B, I'm looking at the sum, so I'm allowed to separate them. Oh my gosh, we're doing calculus, and this is so easy. Whoops, not equals, that's supposed to be a plus sign. So I can write them separate, and then I say, hey, I know this one is 3/2, and hey, I know this one is 1/2, and so 3/2 plus 1/2 is, of course, 2. See you on the next video!